What specific problem does the length-scaled Softplus attention (LSSA) method aim to solve in the context of existing attention mechanisms?
The length-scaled Softplus attention (LSSA) method specifically aims to address two significant problems associated with existing attention mechanisms: numerical instability and the inability to maintain distinct attention peaks for longer token sequences. Traditional Softmax attention suffers from numerical instability due to the exponential function, particularly as model sizes increase. Additionally, as token lengths grow during inference, the attention scores become smoother, which diminishes the model's capacity to focus on relevant tokens. LSSA introduces a dynamic length scale factor that accounts for varying token lengths, enhancing the model's performance and scalability. By utilizing the Softplus activation function, LSSA not only improves numerical stability but also ensures that attention scores remain sharp and distinct, thereby facilitating better length extrapolation capabilities in large language models.
How does the proposed LSSA algorithm work? Please illustrate the step-by-step procedure involved in the attention calculation, including any key formulas used in the paper.
The proposed length-scaled Softplus attention (LSSA) algorithm enhances attention mechanisms by introducing a dynamic scaling factor and utilizing the Softplus activation function. The attention calculation begins with the transformation of queries Q, keys K, and values V into attention scores A through a two-step process. First, the raw attention scores are computed using the formula A equals QK caret T, where QK in math BBR caret L times D and L is the sequence length. Next, instead of applying the traditional Softmax, LSSA replaces the nonlinear transformation with the Softplus function, leading to the formulation A equals text Softplus A, followed by applying the L_1 norm for normalization, ensuring that the sum of the absolute values equals 1. Additionally, LSSA incorporates a dynamic length scale factor, defined as text scale equals log DC dot log n, where n is a matrix reflecting the number of tokens involved in attention, which helps maintain performance across varying sequence lengths. This combination allows LSSA to effectively manage longer sequences, while ensuring numerical stability and improved performance.
Can you provide a specific example of how the LSSA operates on a set of input tokens? Walk through the inputs and demonstrate the calculations involved to show how attention is derived using LSSA.
The length-scaled Softplus attention, LSSA, operates by transforming input tokens through a series of steps to derive attention scores. For a given set of input tokens represented as queries, Q, keys, K, and values, V, LSSA first computes the raw attention scores using a nonlinear transformation, specifically the Softplus activation function, which introduces nonlinearity while maintaining smooth gradients. The attention scores are then normalized using the L_1 norm, ensuring that the sum of the absolute values of each row equals 1, which stabilizes the training process and balances the influence of each dimension in the value vectors. For example, if we have a sequence of tokens with corresponding raw scores, LSSA applies the Softplus function to these scores, transforming them into positive values. Next, the L_1 norm is applied to normalize these transformed scores, allowing the model to focus on the most relevant tokens while suppressing less relevant ones. This process results in a set of attention weights that are then used to compute the final output as O equals AV, where A represents the normalized attention scores. The dynamic length scale factor, which accounts for the sequence length, further enhances the model's ability to manage longer sequences effectively, ensuring that the attention mechanism remains robust across varying token lengths.
What are the theoretical or practical benefits of using LSSA over traditional Softmax-based attention mechanisms, particularly in terms of handling longer sequences and numerical stability?
The length-scaled Softplus attention (LSSA) mechanism offers significant theoretical and practical advantages over traditional Softmax-based attention mechanisms, particularly in managing longer sequences and ensuring numerical stability. Theoretically, LSSA introduces a dynamic length scale factor that adapts to varying token lengths, enhancing the model's ability to maintain distinct attention peaks even as sequence lengths increase, which is crucial for effective length extrapolation. Practically, LSSA demonstrates improved numerical stability by replacing the Softmax's natural exponential function with the Softplus activation, which mitigates issues related to gradient explosion and maintains smooth gradients during training. Empirical results indicate that LSSA outperforms standard attention mechanisms across various sequence lengths, maintaining nearly constant validation loss even at 16 times the training token length. This stability and performance enhancement make LSSA particularly beneficial for large language models, LLMs, that require robust handling of extended sequences.
What methodologies were used to validate the effectiveness of LSSA? Discuss the datasets employed, the metrics for performance evaluation, and how the results compare to existing attention methods.
The effectiveness of the length-scaled Softplus attention, LSSA, was validated through empirical testing using the GPT-2 small architecture, which consists of 124 million parameters, trained on the FINEWEB-10B dataset containing 2 billion training tokens. The models were evaluated using a sequence length of 1024, and performance was assessed based on validation loss across various attention mechanisms, including comparisons with standard Softmax attention and other Softmax-free attentions. The results indicated that LSSA outperformed traditional attention mechanisms, particularly in handling longer sequences, as it maintained nearly constant validation loss even at 8K tokens, while other methods experienced significant performance declines. Additionally, the introduction of a re-weighting mechanism further enhanced the performance of LSSA, demonstrating its superior scalability and stability compared to existing attention methods. Overall, the findings suggest that LSSA not only improves numerical stability, but also enhances length extrapolation capabilities, making it a promising alternative to conventional attention mechanisms.
What limitations or potential drawbacks does the LSSA approach have, especially concerning computational resources and generalizability to larger models?
The LSSA approach, while demonstrating improved performance and numerical stability, has notable limitations regarding computational resources and scalability to larger models. Firstly, the implementation of LSSA and LSSAR using PyTorch's built-in functions incurs significant memory and computational costs, which can be a barrier for practical applications. Additionally, the evaluation of LSSA was constrained to a smaller model, GPT-124M, with a maximum inference token length of 16K due to limited computing resources, raising concerns about its generalizability to larger models with billions of parameters. Although the paper suggests that LSSAR would likely maintain stability for token lengths greater than 16K, the lack of empirical evidence on larger models leaves uncertainty about its performance in such contexts. Finally, the recommendation to develop highly optimized tensor programs, such as FLASHATTENTION3, indicates that implementing LSSA effectively requires a deep understanding of hardware and CUDA programming, which may pose challenges for many practitioners.